Okay, so I will start with a general problem of identity testing, in which case you have two unknown distributions, PQ, you have sample access from them, and they are both on the alphabet sigma. And you want to tell between whether they are equal or whether they are, at least epsilon far away, with probability bounded by 1/3, error probability bounded by 1/3. So in this talk, our target distance is the total variation distance. This general problem is very well studied. It's known that the sample complexity is depends on the square root of the support size, alphabet size, over the accuracy square. Also of interest is the high dimensional case, in which case P and Q are unknown joint distributions on n copies of the variable. Of course, we can apply the general result, but now the effective domain size becomes size of sigma to the nth, so you need to pay exponential in n samples. This is unavoidable because even in the binary case, in which case, and even if Q is known to be completely uniform, it is known that exponentially many samples are necessary. So to get away with the lower bound, we sort of need to impose some additional combinatorial structures on the distributions. So one very useful and flexible way of tuning the complexity and tuning the complexity of the distributions is through Bayesian networks. To define a class of Bayesian network, we start with a cyclic graph G, with n nodes, each representing essentially one variable of the joint distribution, taking value in sigma. And then we need to specify one specific distribution from this class. We need to spell out the conditional distributions. We need, for each vertex V, we need to specify a conditional distribution for each of its possible value, as well as each value combination for its parents. By parents, I mean those nodes with an edge pointing towards V. And given those conditional probabilities, then the distribution is defined by, on a certain configuration X, it is just the product of the conditional probabilities in a topological order with, actual values filled in. Okay, so our work focused on trying to test between Bayesian networks, and our first case is the case in which we assume that P and Q have an unknown but common underlying DAG G, which means that P and Q have this same form of factorization and dependence, conditional dependencies, but we don't really know it. So, but we do need to know the maximum in degree of the graph G, which I will call D from now on. Given that, our testing results shows that the sample actually depends linearly on n. So we do avoid the exponential dependency on n. Okay, but there is an exponential dependency on D, the maximum in degree, which is natural because if D is n, then the DAG G is complete and it can express any probability distribution. So we go back to the general case. So the main application is when D is very small, constant. Then the first factor goes away and the rest looks pretty good. Okay, so the main technique is very simple, actually, which I call a distance localization. Essentially says something like, essentially we want to prove something like, if two joint distributions P and Q are far away, then we can actually find a small subset of vertices S acting as a witness, so that the marginals of P and Q on S are also far away. Okay, so given that, it essentially reduces the original problem to identity tests on those pairs of marginals on those small S. And it has a smaller dimension, so a smaller effective domain size, and we can apply the general result. The key question is which distance to localize in. The most natural choice seems to be the total variation distance, because that's our target, actually. it's very easy to show that TV distance satisfies this subadditivity. So if you look at it, the total variation distance between P and Q is upper bounded by a sum over V of the TV between the marginals of P and Q on essentially the neighborhood of V. Pi V is a set of parents, so neighborhood of V. The second term, it doesn't really matter because it is dominated by the first term, actually. So given this, we can argue, so if P is actually equal to Q, then the marginals of P and Q on S, of course, they are the same for any subset S. But if P and Q are at least epsilon away from each other, then we can find a witness V so that the distance between P and Q on this neighborhood of V is also significant. So the problem reduces. Okay, so also because we assume that the in degree is at most D, so the neighborhood size is at most D plus 1. So so now the problem reduces to testing P and Q on those small subsets. We don't really know those subsets, so we just run one test for each subset of size bounded by D plus 1. And we just do that using the general algorithm known for identity testing. And we output P equal to Q if and only if all those tests pass. The marginals have domain size sigma to D plus 1. So our samples, it gives us sample that is quadratic in N, because identity test is like 1 over accuracy square. So we have the accuracy, which is epsilon over 2n. If you square it and reverse it, you get quadratic, which is good. It's not exponential in N, but it's still suboptimal. We can get linear. So maybe the second attempt is KL divergence. The chain rule allows us to get a similar subadditivity inequality, and we can argue the same way of, if they are far away, then the KL is also far away by Pinsk-Kersey inequality, so we can localize the KL onto some neighborhood. But actually, KL tests require infinitely many samples due to arbitrarily small, low probability elements. You have this log P over Q, so there's this thing in the denominator which breaks things. So our third attempt goes to Hellinger distance, which is defined by this slightly complicated expression. We mainly look at the square Hellinger. It is always take value in 0, 1, and it always also in some sense sandwiched between TV and KL. So we hope it can give us the best of both worlds. So first we need a subadditivity inequality. This is one of our main results, which is to show that Hellinger square also satisfies the subadditivity. So we can localize as before. To test it, we test, we run a test for each small subset. Importantly, Hellinger square can be tested in, essentially 1 over accuracy sample, not 1 over accuracy square. So if you invert that epsilon square over 2n, you get a linear sample complexity. Can be slightly improved by using some more sophisticated Hellinger test. So our result for, in general, we can get linear samples. And we need to run a lot of tests, so that gives n to the D plus 2. But actually, if we know the underlying DAG G, then we know exactly what neighborhoods to test for. So the time, or the running time, also goes to n squared. The dependency is optimal. So very quickly, for trees, if just now we assume we look at the underlying DAG is the same, but now what if they are different? So we also study the case in which the underlying DAGs are different trees. And we can actually find a common DAG with a constant in degree that admits both trees. And this is actually a purely combinatorial result that shows that it is possible. We can always find a DAG of in degree 5 that admits both trees, no matter even if they are different. So then the problem reduces to the original problem, because it's just a DAG with degree 5. So we get this result with linear dependency on n and polynomial running time, which is also optimal. That's it.
Thank you. Satyen, question?
Sorry, is there any hope of reducing the constraint from 3/4 to 1/2 index on it?
3/4 to 1/2.
1/2 would be optimal.
Okay, so this is by a paper written by someone else, and I think they claim that it is actually optimal. It is a lower bound.
Because it deals and
Right. Yeah. So probably 3/4 is optimal if we are using this result. I don't know too much about it, but I think they claim that.
All right. So I think Qinxuan again.